Okay, YouTube, in our last couple of videos, we've been solving logarithmic equations by getting the logarithmic expression by itself and then just rewriting it exponentially. But in our last video especially, we looked at situations where there isn't just one logarithmic expression to get by itself, but several different logarithmic expressions that we had to write as a single log using our properties of logarithms. That works. It certainly works in this video. If we were to get all this equal to 0 and use our properties of logarithms, we could rewrite this expression in an exponential form after getting the log by itself. But in this video, what I want to focus on is what we call the one-to-one property of logs. So being aware of the fact that we've looked at the one-to-one property of exponential expressions, that is to say, if two things with the same bases are equal, then that's only true if their exponents are equal. So for logarithmic expressions, we say the same thing. Log base b of a capital M here would be equal to log base b of a capital N if and only if their arguments of these logs have to be the same. So what this says is if you would like to, if it's a situation where this actually applies, we can express the equation in this form, log base b of m equals log base b of n, where two logs are equal with the same bases. And then we could make the statement, well then, it must be true that m is equal to n. And at that point, we could solve for whatever the variable is. And the number 4 here says definitely want to check for the proposed solution. So let's take a look at this equation here and see how we could use the one-to-one property to solve it. Now the one-to-one property only works if we have two logs that are equal to one another, exactly equal at the same bases. So what I notice here is that I have the ln of x minus 3 on the left side of this equation, but just two logs on the right side. So our first effort is going to have to be at condensing these expressions right here. So we're going to condense these two logs, and I notice using my properties of logarithms here that when you subtract two logarithms, we could write that as a single logarithm of the quotient of these two arguments. So we'd have 7x minus 23 all over x plus 1. And in this case, we could see that because I have a natural log equaling a natural log, then it must be true that their arguments are the same. So what we're going to do is we're just going to work out our algebra here. But we know that x minus 3 has to be equal to 7x minus 23 over x plus 1. So as we do when we solve rational equations of this type, what we usually do is multiply both sides by the least common denominator, which in this case is just x plus 1 there. So x plus 1 is our LCD. On the left side, we're going to get x plus 1 times x minus 3. On the right side, we're going to get, well, 7x minus 23. And the reason why is because that factor here, x plus 1 over 1, canceled with our 7x minus 23 all over x plus 1. So let's go ahead and distribute on the left side here. We get x squared minus 3x and plus an x, so minus 3x plus an x minus 2. And on the right side, 7x minus 23. So combining like terms, all said and done, on the left side, I believe we have x squared minus 2x minus 2 equals 7x minus 23. And as we do when we solve equations, we want to set this equal to 0 and probably attempt to solve it by factoring. That's usually our first method that we check here. So plus 23. 23 here. Oops, this should be a minus 3 here. A minus 3. Sorry, thought I had missed something there. So when we get this on the left side, the right side's cleared. We have a 0. We have x squared minus 9x plus 20. And if we solve this, of course we'd do it by factoring. We'd say this is x minus 5 and x minus 4. So if that's equal to 0, of course you know if your linear factors are x minus 5 and x minus 4, then your solutions are x equals 4 and x equals 5. So I do want to check this out. If we plug 4 and 5 back in for x, do we only get positive things inside of the arguments? Because one important thing to check is we can, the solutions here, but it can only include solutions for which m and n, or whatever the expressions are in here, as long as they're positive. So if I put in, say, a 4 minus 3 is 1, that's positive. 4 times 7 is 28, minus 23 is positive. And 4 plus 1, that's positive. So you can see how putting in a 5 also is definitely going to also be positive. So both of these would be the solutions to this particular equation. Cheers.